we are moving forward to the next speaker. Okay, our next speaker, okay, Alex is here. Our next speaker is Alex Bäuerle. He's a PhD student at University, Germany. He's an expert who works at the intersection of visualization and AI. He primarily investigates how to make AI technique more approachable, more interpretable, and more trustworthy using visualization, which is a hot topic nowadays. During his PhD, he also had the chance to work on the topic with different teams at Google. So Alex will introduce us visualization for AI in critical domains. Let us welcome Alex and enjoy the last lecture of the spring school. So Alex, the floor is yours.
Thanks, and thank you for the warm introduction. Yeah, I'm going to talk about how visualization can help the hot topic, as you called it, of AI, and how, especially in critical domains, such applications really benefit from incorporating visualization. And to start that off, we can ask ourselves the question, yeah, why do we need visualization in that space? And to give you a bit of a warm-up, like we all see how AI is growing rapidly right now, and especially in the field of biology and medicine, we see a lot of growth and a lot of interest in these techniques, and that's probably rightfully so, because AI has opened doors that weren't open before, right? We can do stuff now that we couldn't do before we incorporated AI into our applications. But at the same time, this includes also some big unknowns and some danger. And to illustrate where this comes from, I made a small example. So this is a very simple function, right? And we could probably easily understand what it does and follow if we put something in there, what would happen. It's not a lot of parameters. It has like one nonlinearity, and it's pretty simple. But if we look at neural networks, and this is a very simple example for a neural network. So this is only 2 conv layers, and one pooling layer and 2 dense layers. This is something that you would probably program as one of your first exercises when you get into deep learning, to solve something like the MNIST task, where you classify handwritten digits from 0 to 9. But already this very simple model has over 27,000 parameters. And so here we're kind of lost with understanding the function that this model approximates. And if we then add to this fact that we're not able to fully understand what happens inside this model, if we add to that fact that this model, or such a model, maybe something a little bit bigger, but such models make very important decisions. So for example, if you're in the medical domain, you might feed your model some metadata, or maybe a CT scan or something. And it tells you, yeah, you should get a surgery or something like that. It makes a prediction and a recommendation for a treatment, which is nothing that's out of the reality. Then we really understand why it's important to look into these models and to try to make them robust and make them a little bit more understandable. And to give you an introduction of the work that's happening in this kind of domain to make models more robust, more understandable, to really grasp what's happening, I'm going to talk about 3 main visualization areas in this modeling pipeline. Yeah, and one of those is data, both going into the model and going out of the model. We're operating on large training data sets, and we're also doing a lot of predictions with these models. Then we're talking about features, and that's basically what the model learns and how to understand that and how we can visualize that. And then I'm going to talk about models themselves and how to communicate architectures and incorporate some of these visualizations into the model context and visualize where things are actually happening. And so let's start off with data, visualizing data for AI. And when it comes, or for this one, I'm going to give you some examples, and they're going from very general data visualizations to very specialized ones. But first, let us talk about some general questions we can have about data. And those very high level questions, and you could dig deeper here and ask a lot more questions, but on a very high level, we want to know what data do we actually have, what are we working with, both what data goes into the model, but also what is the model producing, what are predictions, and then how are they distributed, how is my input data distributed, how is my predictions distributed, and what kind of data performs well or bad, so that I can kind of get an idea of where my model is good and where it's bad, where I might need more data, or where I probably can't use the model because it won't perform to my expectations. And since we're operating on this high-dimensional space, what we're often doing in this domain is using visualization techniques such as aggregation, dimensionality reduction, or clustering. And so for the first example, which is a pretty general data training data visualization, I'm going to show you the embedding projector from Google. And what you can do here is explore the data that goes into a model, or in this case, you explore what the model, what kind of different tokens the model can actually see in this word embedding from the point of the model. So what you do is you feed your data into the model, and then you get some intermediate embedding, and then you can project this embedding to 2 or 3 dimensions. In this case, 3 dimensions. And I've hovered here this Euclidean label. And if you would hover other labels around this one, you would see other math-related labels be positioned close to that. So this way, you can already kind of get an idea of how your data is distributed and what data you're actually working with. And so I mentioned that this is a very general application. It's not really focused on any specific application use case. It's not like you can use it for fairness, you can use it for just plain distribution analysis, you can use it to see if your model actually learned something. So there's a lot of different applications that you could do with this one. And then getting a little more specific is Know Your Data, which was actually presented just this week at Google I/O. And here, Google presented basically a very powerful filtering visualization, where you can do cross filtering between a lot of different attributes, and look at image examples, and also see, as displayed in this example, how specific metadata correlates with each other. So in this case, some object labels are classified with higher confidence, and some are classified with lower confidence by a model. And so here it gets a little more specific. The authors of this one say, Know Your Data helps researchers, engineers, product teams, and decision makers. So yeah, still a lot of people, but for example, what's missing here is the end user. So it's really for people who are working with this and developing this and making decisions for deployment. And this tool helps understand data sets with the goal of improving data quality and help mitigate fairness and bias issues. So yeah, this tool is really special, or is really focused on improving the data quality that you're working with. So slightly more specialized, but still a very generally applicable tool in the space of yeah, AI data visualization. And then as a last example, I'm gonna present something that we've been working on in our group. And here we were looking at how to detect and remove labeling errors from data sets. And for this one, we identified 3 different types of errors that can possibly, or that are likely to occur in the context of labeling data. And when I'll talk about a labeler, I mean either a human person annotating an image or a data point, or an algorithm doing the same thing. So a labeler can really be anything that assigns a label to a data point. And we identified that very common error types are first class interpretation errors, where someone confuses one class for the other and assigns all these labels of the one class to the other. So maybe you're not good at differentiating dog breeds, and you think one dog breed is the other dog breed, and so you confuse those labels and mislabel all the samples from that one. And that would result in many samples of that type being misclassified as the wrong class. So in this case, at the very top, so this is a intentionally corrupted data set. At the very top, you see that a lot of samples that were labeled as 4 were classified by the algorithm as 3. And yeah, now we can look into that and see if that's actually a model performance problem or if it's a data problem. And then for the second type of error, which we called instance interpretation error, where you only mislabel one single instance, we're really about spotting the outlier in the data distribution. And so we do 2 things. First, we visualize the distribution of probabilities of misclassifications. So you see these small red bars in this matrix view. And if the bars are at the top, the model is very confident about its misclassification. And this confidence might be a hint to potentially mislabeled samples. So you might want to revisit those first that are very confidently misclassified. And then we also use dimensionality reduction to, if you go into one of these cells and look deeper, or yeah, look deeper into one of those misclassified collections, then you can see such a projection visualization where, in the optimal case, the sample that's mislabeled is positioned far away from the other samples because it has different attributes or different features than the other data samples that are correctly labeled. And the last one is similarity errors, and this one can be problematic for 2 reasons. First, if they're across train and test data splits, then you're not evaluating on independent data. And that's really a problem, because then your network performance, your reported performance, won't match the real performance of the network. And if it's in the same data split, so if it's only in test, you have duplicates only in tests or in train, then you're reducing your effective data set size. So if you have lots of duplicates in the training data, then you're effectively training on a smaller training set. And so it can be desirable to remove those. And we use simpler or standard computer vision approaches to detect these duplicates and surface those with this duplicate icon. So to wrap this data part up, we went from very generally applicable data visualizations, just dimensionality reduction, to something that's really focused on cross-filtering by metadata, to something has a very special application context with correcting errors in dataset, and is only designed for this one task. Yeah, and so as you might see, this data visualization space in general for neural networks is pretty large, and you can do lots of different things here. Going to the next one, we want to look into how, and give an introduction into how we can visualize what a model actually learned. And this is a lot of explainable AI happens in this context, trying to explain what features a model picked up. And to give you a very prominent example of that one, I want to explain a little bit how gradient-based saliency approaches work. And so in general, for saliency, what you want to do is you have an input image X, and you have a model that maps this input image to some other representation. In this case, it's a classification model, but you could use a different model here. And the saliency technique is really something that maps from this input image to an explanation of what are salient features in this input image that are important to a specific part of interest in this model. And the general approach of this is pretty simple. what you do to calculate these feature important maps or these saliency maps is you calculate the gradient of the model with respect to the input that you're interested in. So you feed the input to the model, get the gradients, and backprop them right into the image domain and see where the gradients kind of resolve to in the input image. And then when the gradient value, when the absolute gradient value is either is very high, then you know that this specific, in the image case, pixel, or in tabular data, it would be a column of your data. But in the image case, you see that if a absolute gradient value is high for a certain pixel, you know that this pixel must be somehow important for the prediction, because if you change that pixel, then the prediction would change. That's basically what the gradient value is telling you, right? If the gradient is high, I change something, that's something that will result in a big change in the output. So that's the basic idea of gradient-based saliency, and we can do that at different granularities. So we can look at individual neurons. Oftentimes we want to look at the prediction output for a specific class, what made the model predict that class. But we can also be interested in neurons in the middle of the network, in entire layers, or in, for example, channels for convolutional layers, to see what they're really looking for. And this was a very easy approach that I presented, but there's been a lot of follow-up work, and one really interesting I find is X-ray. And the trick they're doing here is it's a very simple but very cool idea to use superpixels before applying these saliency techniques. So you split your image into superpixels, then you do the same saliency, or they use integrated gradients, which is the slightly more complex saliency technique, but it's also based on calculating the gradient. Do that back to these superpixels, and then you pick a threshold for those superpixels by importance, or by how much of the gradient ended up in the superpixel. And then you can have these really nice explainable regions instead of these pixelated, highlighted images that are not really super interpretable. And if we go one step further than just like calculating feature or the attribution, if we don't just calculate the gradient, but if we also apply it and do that iteratively, what we can do is we can actually increase the activation of a certain neuron. So if we calculate the gradient, we know what we need to change to make this activation different, either higher or lower. And so by iterating over this and repeatedly changing the input, we can make the neuron either activate very, very much or don't activate very low. And what we end up with is something like these images, if we do it for images. And you might know those as either feature visualization or deep dream. And yeah, what this really tells us is what is a certain neuron or certain structure we are interested in the network. What is it looking for? What is highly activating this neuron or this output or this layer of the network? So that was the feature-based approaches that I wanted to present today. And for the final section, I'm going to talk a little bit about visualizing neural network architectures or models. And here I'm going from more abstract to more simplistic, more abstract visualizations to more complex, more feature-rich visualizations. And so for the first one, I want to again show some work that we did. And what we observed is that the number of papers in which figures of neural networks are presented has been kind of exploding over the past years. And we extracted all these figures from these computer vision conferences and annotated them by hand with different features. But we noticed that all of them, or almost all of them, were handcrafted and non-uniform. Like there was no like uniform design language. And then after we annotated these figures, we went and talked to some of the authors of such publications. And what they also told us is that, yeah, this figure work is very time consuming, and they would rather spend this time on optimizing the model. And since you probably can imagine that generating figures for your publication is the last step before submitting, this can also be error prone. And yeah, machine learning experts generally would like to be relieved of a lot of this visualization handcrafting. And so what we did is we created an approach to make this more automatic and easier to use and easier to generate these figures. And with BioMedVis, you can simply paste your code into this web page, and then you automatically get your network visualized. You can group layers. The design of the layers is informed by visualization knowledge. So we use width and height of the layers to communicate spatial dimension and feature channels. We saw a lot of 3D visualizations in the deep learning papers, and we asked the authors and other participants of a study, and they confirmed that this 3D doesn't really add value. So we went to 2D and we did other visualization improvements. And so with this one, you can get a unified design language really easy by just pasting your code, doing some visualization adjustments to make it fit your need for the paper, and then yeah, just have a publication ready figure in a few minutes instead of handcrafting it for hours. And what's cool is that we've actually seen some adoption of this already, and especially in the medical and biological domain, we see that people are picking this up and liking this, since they're still kind of hand programming their models and really craving for such a visualization tool. But I've already said that we want to go from simplistic to more complex visualizations in this model architecture visualization space. And so next up, I want to show you some more complex and maybe developer-oriented figures, instead of before we were oriented in communication of the model. And so now here we see TensorBoard, Netron, and Netscope network graphs, and they're really yeah, much more complicated. They're much larger. They won't fit on a single page for a publication, but they also have information about initialization, about kernels, about the weights in the model. If you look at it, how they're initialized, how they're computed, and all this kind of information. So this is really a much more in-depth visualization that's focused on a completely different audience. And then if we combine such network architecture visualizations with approaches that I presented before, so for example, feature visualization and also embedding techniques, data embeddings, then we get something really rich like this summit approach, where you can really explore the model, important layers of the model, and see the features that the layers learned, see where data fits in the embedding view, see data examples. And yeah, if we start combining these visualization techniques, we can really craft these very powerful, also expert tools where you can explore model really in depth. Cool. So to summarize, I presented you visualizations from 3 areas here: data for neural networks, features that they learn, and models. But what it was really about, and what I've heard in a bunch of different talks already at this spring school, is that it's mostly about going or starting from a problem that you see and trying to find a solution for that problem. And oftentimes for AI, this can be a solution. So if you want to communicate your models, you might use something like BioMedVis. But there's a lot of different visualization going on. So there's very different data, very different target audiences, and very different tasks that we have in mind for these visualizations. But all in all, it's about trying to solve a problem that you see in the space, and use this to get to a better solution. And to kind of reiterate on what I said at the beginning, that there's a lot at stakes in this AI domain, especially if we apply it to critical application tasks. Whenever this happens, wherever there's a lot at stakes, visualization really shines, I feel like. And we've seen that in COVID as well, like a lot of charts, and in the talk just before for this one, we've seen a lot of COVID visualizations. So there's another area where the visualization was really on the up. And yeah, and I think what we need to keep in mind in this context, also in the AI context, I was really inspired by this viral visualizations paper that was presented at Kai last week. And what we can keep in mind for this, I think, is that we should try to tell the right stories and work on shape the perception of AI in the right way, so that we surface the problems that it has, but also make sure that where it works and where it's good to use, that we promote it and that we show what it can do. And with that, I'm at the end, and I'm happy to take questions.
So thank you very much for the very insight talk. And we have a couple of interesting questions in the chat. So let me read one by one for you. So the first question was from Havik Hauser. He's asking, in so many classification example, there is an implicit assumption that only one label is correct for variable X, for example. However, all too often, that is not according to the real world, where X can have multiple labels that are all correct, depending on the perspective. Why are we so much focused on one-to-one X label relationships?
Well, I guess we've been focused on that because it was probably easier. But I also think that a lot of focus shifts to these more complex label spaces, where not only one label is correct, but maybe an image can have multiple labels. There are multiple objects in it, and you can have all of these, and maybe not one thing is true, but multiple things can be true. Yeah, but I think so far we've seen a lot of visualizations for single label problems, or for one-to-one mappings, as you call it, because it's just, I guess it's a natural entry point. And yeah, there's a lot of work going on around this multi-label classification space. Yeah, but I think we have to wait a few more submission deadlines, and then we're going to see much more of this type of work.
Great. That means it's an increasing research topic, and we are all interested in that.
I think so, yeah.
Great. So let me move on to the second question. It was asked by Ernesto Avila. Using visual representation for AI interpretability, how can you avoid over interpretation, seeing things because you want to see them and not because they have actual meaning?
Yeah, I think that's a very good question. I guess every time we simplicate something, and that's, yeah, I guess that's what we're doing if we're looking at parts of a neural network, or if we're abstracting it, if we're reducing dimensionality, and we're always prone to this danger of misinterpreting things. I think one way to counter that is to use those explainables and explanations as hypotheses, and then try to verify them with different visualization approaches, or with different algorithms or techniques. But yeah, we have to be very cautious of, especially kind of in this feature visualization domain, there's a lot of interpretation going on, and yeah, we need to be cautious not to overinterpret. I agree.
Thank you. So we have last question. I think it's very interesting. It's from Paco Ubrich. Have you deal with explanation of neural network decision making to audience with zero computer science background?
So sorry, I didn't get the second part.
So he was asking, have you have you ever explained neural network decision making to audience without computer science background knowledge?
I mean, not in I for myself, not in a publication, but I think, for example, if you know TensorFlow Playground, that is something that can be used to explain something to laymen or to non-experts in this domain. So I think there's some work, and also in the medical domain, there's work focused on explaining the decisions rather than really explaining what the model internally does. You don't really know the model, but for example, yeah, in the saliency visualizations, for example, you can see, okay, this has a lot of importance, and this can be understood by anyone. You don't have to be a neural network expert to understand that. I would say so. Yeah, I think there are visualizations that can be used for audiences without machine learning backgrounds.
Yeah, I also think so, because we are now using AI for a lot of application domain. Definitely, the public is also having interest in understand the basic concept behind it. So I think we are running out of time. So I would like to invite Alex later. Maybe you want to discuss with people in the chat as well. And we are having, I'm sorry, I'm a bit over time, but we will have 10 minutes break. But I would like to let you know that we will have very interesting closing session and also social event afterwards. So let's come back in 10 minutes. Thank you. See you later.
Thanks for having me.